about optimal discrimination of two-qubit states.
Okay, thanks Richard for the introduction. So today I'm going to talk about two papers that we put up on arXiv this year. This is a joint work with Eric in Southern Illinois University and Ren Yao in the audience and myself. And Ren Yao and I were with University of Technology Sydney right now. Okay.
Choose your microphone.
Yes, I think so. The red eye is on.
Should be green.
Okay.
Maybe it should be
Should we green?
I don't know, that's usual. Oh, that's off. It's fine.
Oh, it's fine. Okay. So I would first like to thank the organizer, of course, to bring up this such a wonderful program to bring us here. And I would also like to share my favorite quote since we are in Isaac Newton Institute right now. And this quote is by chance from Isaac Newton. And he says that if I have seen further, it's by standing on the shoulders of giants. When I first heard of this quote, I was young and I don't really understand what it means. But like after roughly 7-8 years of researching, and I kind of know what it really means. And the more I study, like the little I feel that I know about the whole, just like the whole knowledge base of the science. And then especially when you realize that when you are working on some problem and then you realize that you can just apply someone's approach and suddenly you can solve this problem, like that has been bothering you for such a long time. And this is when I realized how true this quote is. Okay, so back to the scientific part. So this is the outline of today's talk. So mainly I would overview our results in these two papers that we put on arXiv. So we have like 3 main results in these two papers. And then if I have time, I would also share with you some of the new development that we have regarding the asymptotic LOCC stuff. And then with that, we can construct an example that shows there's a gap between separable norm and LOCC norm. I think some of the people in the crowd might be interested in this. Okay, let me move on to the first part. I would start from the basic. I would start slow, and then in this talk we would look at the state discrimination problem, and we would mainly look into 2 settings. The first setting is the minimal error probability setting. So what does this mean? So given an ensemble, so fix an ensemble, and then the total identification success probability with respect to the P of M is given here. So it's just sum over I from 1 to n pi trace of pi I rho I. And then the minimal error probability is defined to be you take the minimization of all the measurement P of M of 1 minus pi of E. And then the second setting that we would use is this minimal inconclusive probability, or you can also think of this as the unambiguous discrimination case. So in this setting, you have an additional measurement outcome that corresponded to the inconclusive probability. So whenever the outcome happens, it would always be true. But the price you pay is that with certain probability, you would have this inconclusive outcome 0. And in order for this, you need to have this additional condition. So pi I and the measurement P of M for the I outcome must be orthogonal with the jth element in your ensemble for I not equal j. So we will mainly talk about state discrimination in these two settings. And then we were also interested in this LOCC, local operation and classical communication setting. So I believe most of you understand what this means. This is just the party was separate in space, and the operation they are allowed to perform is just local operation, and then they have the classical communication are allowed, and then it goes like as follows: like Alice prepared the first measurement, and then based on the outcome I1, she sent this outcome to Bob through this classical communication channel, and then based on this classical message received by Bob, he performed another set of a quantum operation, and it goes on and on. And one subclass of this LOCC protocol is the so-called one-way LOCC. In this case, you only use the communication once, and we would assume it's from Alice to Bob, and we have some result later on this one-way LOCC protocol. And then a very famous phenomena that is closely related to state discrimination is called the non-locality without entanglement. So this phenomena was formally introduced by Bennett and his collaborator in this big paper in 1999. And in this paper, they construct a Q-trick ensemble. Now we also known as the domino state, and this state are orthogonal to each other, and they are in the product form. The interesting thing is that with this domino state, they can show that if you allow your measurement, like you perform your measurement jointly on this bipartite state, you can retrieve more information than you are only restricted to perform the measurement subject to this LOCC setting. So in a sense, that and actually the measurement that are optima are the separable measurement. So they also establish this statement that LOCC is a strict subset of separable operation. And then another important consequence of this phenomena is that entanglement is different from non-locality, because you see in this example the state are in the tensor product form, but you need to have a joint measurement so that the measurement acts jointly on the system in order to extract more information. So yeah, and then we will return to this phenomenon by constructing more examples that demonstrate this non-locality without entanglement property. Okay. So now I would going to move to our first result on the double trine ensemble. So first, let me define what the trine state means. So the trine state ensemble consists of the following three states with equal probability, and it's easier to see from the picture. So this is the XZ plane of the Bloch sphere, and the trine state spacing evenly on this xg plane. So if you perform a rotation of 120 degree on psi 1, psi 0, then you will get psi 1. Likewise, if you apply this rotation on psi 1, you would get psi 2. So they have this covariant structure. Okay. And this example, the tri-state was first defined in this very famous paper by Paris and Wouters.
Actually, I don't think that's right, because
Oh, really? Holevo was the first.
Years earlier,
Oh, okay. But they first construct this double tri. That's
I guess.
like then. Okay. So let me correct this. So the tri ensemble was from Holevo according to Richard. But I think for the double tri ensemble, it was first.
I think that the trine is also a special case of a frame which was used by signal processors for a very long time.
Oh,
I think so. This is
This
very
is
simple.
quite simple even in middle school, right?
Yeah, even
car manufacturing.
yeah. So anyway, this is a very simple example. Yeah, and then they actually define the so-called double tri ensemble to be the source create the identical copy of the tri-state and given to Alice and Bob. So this is the so-called the double tri. So what the original problem is in this Paris and Wouters paper. So in the paper they asked two very instructive questions concerning the double tri ensemble. They can apply to any measure of distinguishability. So what are the questions? So they have two conjectures. So the first conjecture is that they want to demonstrate that LOCC is strictly suboptimal compared to the global operation. And then the second question they ask is that is one-way LOCC is strictly suboptimal than LOCC. And in the paper, they choose a very difficult to handle. They choose the accessible information because it defines in terms of mutual information and it's nonlinear. So it's very difficult to handle to compute. And in the paper, they provide numerical evidence showing that these two conjectures are true for the double tri with accessible information as your measure of distinguishability. Okay, and from here you already can show that this numerical evidence shows that the double tri ensemble already have this property of non-locality without entanglement because it's a product state ensemble and LOCC is strictly suboptimal. You need joint measurement in order to extract more information from this ensemble. Okay, then the reason that we start looking at this paper is that we realize that there are many interesting results comes from this paper. So the first one is that it leads to the discovery of teleportation. Of like the idea actually comes from the paper, I think. Right?
That's true.
Yes. Yeah. and then this is the first paper that introduced this LOCC paradigm and studied as a restricted class of operation. So it it's very instructive. They ask very instructive questions. And then, as you already see that this quantum non-locality without entanglement can trace its root directly back to this paper. And actually, in this paper, they have a long discussion and they have a long discussion on this Paris and Wouters paper. And then this data hiding is also one of the, it's basically they ask the same question. So the data hiding is a scheme that you want to hide classical message in the quantum state, so that when you distributed your quantum state in space, then you can only recover perfect or more information by joint measurement. But if you are only allowed LOCC, you cannot extract many information. And in fact, they can show that the information that you can extract decreasing in terms of the dimension of your system by LOCC. So you can show a huge gap. Okay, and then it also influence entanglement manipulation and entanglement theory. Okay, so this is our result on the double trine. We show that with respect to the minima error discrimination, we can have this kind of behavior. So the global measurement is equal to the separable measurement, and is strictly greater than if you allow your measurement to be implemented by LOCC, and is strictly larger than one-way LOCC. I would like to say a little bit about how we get this. It is well known that because the double trine ensemble have this covariant structure, so the optima POVM is the so-called pretty good measurement. So if you don't know that, I think that's fine. But the pretty good measurement is optima. And then you can construct separable measurement from the pretty good measurement by mixing the element from pretty good measurement with the element that live in the orthogonal complement of the space spanned by the double trine. And you can think of that state is one of the bare state. Or this state is the state that span the anti-symmetric subspace of the 2x2. And then by mixing the pretty good measurement and this bare state, you can construct separable state that also attain the same probability as the global measurement. And then the way we demonstrate the LOCC, the one-way LOCC probability, the optimal probability that can achieve by one-way LOCC, is that we somehow make use of the covariant structure of the double trine, and then we perform some cost-graining and apply Hailstrom bound to give a bound on the error probability that for the one-way LOCC protocol. And later on, we actually construct a measurement so that you can attain this upper bound. That's how we demonstrate one-way LOCC is optimal, is to show that. And it's actually a very, very simple protocol. Is that the way to attain this optimal error probability by one-way LOCC is that actually as is to perform some sort of I call the rejection POVM, which is if this is the double trine. So that means that when you have outcome I, that means that the ith ith element is excluded, and then based on this outcome, Bob can further distinguish between the remaining two. So I mean the one-way protocol is very simple actually, and then the way we demonstrate the gap here is using some lemma that I will present later on. So I would skip this part and return to this part later. And then in order to show this, it's also not very surprising is that because this unambiguous discrimination, it's some sort of semi-definite programming, and because of the covariance structure, you can parameterize your measurement and just compute it. And then for separable, you can add more constraint because in the 2x2 setting, the condition for separability is equal to the condition for the PPT is equal to the PPT condition. So you add more condition into your semi-definite program, and you can just compute the error probability. Okay, so these two are just brute force calculation, and then actually here we just use the same one-way strategy, and when you use it, the error probability would give you the same error probability as you are allowed to use separable operation. So that's why one-way LCC can attain this separable operation, and then this equation here is just trivial. So I mean, when you look at this result, when we look at this result, we somehow got worried because with respect to different measure, and you will have completely different behavior. So it's equal, greater, and then this is greater, equal. So somehow we trying to, we have this question that we do not know. I mean, mainly we are worried that this non-locality without entanglement is not a property of the ensemble itself, but it may be depends on the measurement that you use. And if that's the case, then it's not a good thing for this phenomena. So the question that we would like to ask, and we actually put it as an open question in our paper, is that does there exist a product ensemble for which this LCC is strictly suboptimal with respect to one measure, but it would be equal with respect to another measure? I mean, if we can construct this kind of example, then non-locality without entanglement is not a well-defined property, I would say.
So I just want to clarify. So your theorems, the equalities, are those claimed only for the double trine ensemble?
Yes. Okay. Okay. Now let me move on to the second result. So here we look at perfect discrimination of just 2x2 system or 2-qubit. So we only look at perfect discrimination of 2-qubit ensemble. So the first thing that I would like to mention is that in order for ensemble to be able to be perfectly discriminated, the state in the ensemble must be orthogonal to each other. And then with this in mind, there are only 1, 2, 3, 4, 5, 6, 7. There are only 7 different kind of situations if you classified the ensemble by the rank of the state. So what this means? So this means like this ensemble means that you have 2 states. Both of them are rank 1, so it's pure state. For example, here you would have 3 states, and 2 of them are rank 1, so means that 2 of them are pure state, and the other one is a mixed state with rank 2. This is how, and then this is the all possible situation. Okay, so the first result here is is very counterintuitive. So it was done by Wargett, Tony Short, Hardy, and Victor. They actually demonstrate that any two pure state, entangled or not, can be perfectly discriminated by LOCC if they are orthogonal to each other. Okay, so this is in year 2000, and then later on, Wargett and Hardy extend this result to three pure state and 4 pure state case, and in these two cases, the condition is that as long as for the 3 pure state, as long as two pure state are product state, then this ensemble can be perfectly discriminated by LOCC. And then for the 4 pure state case, this 4 pure state must be all product state. And then later on, a result by Runyao and his collaborator in 2010, they have a very nice necessary and sufficient condition, saying that an ensemble can be perfectly distinguished using LOCC if and only if this condition satisfied. So what does this mean? This SCH perp rho, this is the orthogonal Schmidt number. It is defined to be the minimal number of product orthogonal state such that the span of this orthogonal product state contains the support of rho. Okay, so literally, this condition solves the necessary sufficient condition for all cases. So it's very powerful. And then later, and also in 2009, Runyao and again with his collaborators, they look at perfect discrimination of this 2-qubit case using separable measurement. And for example, you can see that for the 3 pure state, the condition is very, very different. So separable distinguishability is possible if and only if, let me first explain what this means. So I think you cannot see, I have it here, but you probably cannot see. So there is a one-to-one correspondence between a pure bipartite state and the matrix representation, a 2x2 matrix representation. So this is what this psi without ket means. So this means that they are a 2x2 matrix corresponding to this pure state. Okay, so the first condition is that the matrix, the 2x2 matrix psi I phi inverse must has 2 anti-parallel eigenvalue. So by anti-parallel, I mean the 2 eigenvalue was related by a negative number. Okay, and then the second criterion is that the concurrence of the state, the sum of the concurrence of the state from the ensemble is equal to the concurrence of the state that live in the orthogonal complement of the subspace spanned by this state, psi I. So a condition like this is very nice because it's easy to check. So given arbitrary ensemble, you can just plug in, compute the concurrence, and you would know like if this state can be perfectly distinguished by separable or not. So it's very nice. And then when we work on this problem, like we only noticed that the only case missing in Runyao's paper is this 1-2 case. So you have one pure state and one mixed state. And actually this problem is also brought out to Eric and me by Runyao. So and then we kind of have a joint discussion here, and we could solve it. And actually, it's very interesting is that in this email exchange, Runyao bring up this question, and then in the following email, he said, "Okay, I kind of know how to do it, and he solved it in less than 24 hours, I think." So it's, and then so let me so this is a statement. So let psi be orthogonal to the rank 2 state rho with phi, capital Phi, being orthogonal to this both state. Okay. So this ensemble can be perfectly distinguished by separable if and only if psi is a product state. In this case, it's trivial. If it's not a product state, then you need to satisfy these two conditions. So it's very similar to the previous condition, except here you only look at the concurrence between psi and the concurrence of the state that is orthogonal to these two. And then if this capital Phi is a maximal entangled state, then this is trivially satisfied because the concurrence is 1 and is the largest. Okay.
So I have two questions. When you say psi-phi inverse, do you mean the projections?
No, this is the matrix representation. So given a pure state, can you see? So given a pure state, you could have this matrix representation through this maximally entangled state. Oh. So this is psi and phi here without ket is a 2x2 matrix. It's a okay. And then we can even show that.
Second, what do you mean by anti-parallel eigenvalues?
Oh, so because the eigenvalue of this matrix could be complex, so it's arbitrary. And then by anti-parallel, I mean that these two eigenvalues can be related by a negative number, by one negative number. So it's if G1 and G2 are the eigenvalue of this psi phi inverse, then they are anti-parallel if and this C is negative, is a negative number. Okay, and then we can show that if in the second condition it becomes equality, then this would give us the perfect discrimination for LOCC. And it's kind of nice, it's because then these two theorems will allow us to construct more examples that satisfy this non-locality without entanglement. If you can construct the concurrence of psi is strictly less in one case, and in the other case, if you can show it's equal, then you could have more examples. So I would return to this later on. So there might be okay. I might want to skip this, but the way I mean the main idea in the proof is actually because this 2x2 is such a small space, and we know the structure very well. For example, we know what the separable operator would look like, and then again, if it's rank 2 and it's separable, like you can always express as a statistic mixture of two pure states. Like very, I mean, it really boils down to because this is small and the property of the product structure and the separable structure is clear. And we also make use of variance stuff, like for example, in this 2x2 case, PPT is equal to separable. And if an operator, say an operator E and its partial transpose in this 2x2 case can be related by a unitary, some sort like this various technique. So yeah, I would prefer to skip it. Okay. So let me move on to the third result. So instead of perfect discrimination, here we look at optimal discrimination. And the states are not necessarily orthogonal to each other anymore. So we only look at linearly independent ensemble. So we have one technical proposition, or it's basically it's more observation than any proof. Like we basically from the proof here. So the result in these two papers is that for linearly independent pure state ensemble, the optima POVM are the rank 1 orthonormal projectors. And from that, you can already observe that if this is the case, then this rank 1 orthonormal projector must be able to perfectly distinguish the orthonormal basics that make up this rank 1 projector. So it's not a surprise. But the implication of this proposition is that then we can somehow transform the perfect optimal distinguishability to optimal distinguishability of non-orthogonal linearly independent ensemble to perfect discrimination of orthogonal ensemble. So this is the main idea. And then later on, we generalize this to a set of mixed state. And then the criterion is that instead of there exists a unique orthonormal basics, then there exists a normalized subspace projector, and then you can perfectly distinguish this normalized subspace projector, and it's in the second paper. So we can actually, I mean, with this lemma, we can already show that consider an ensemble of a linearly independent 2-qubit pure state ensemble. We already can say that a LOCC protocol can optimally discriminate this ensemble if and only if this unique orthonormal basis contains two product states. So you see, so the idea is that you transform this problem to perfect discrimination of this orthonormal basics, and then you just use the result from Worgat and Hardy, then you could already get this. And if n is 4, then all the state here must be product state. Again, from Worgat and Hardy. And then, I mean, then we could, so this is also very simple, I mean, not difficult to see, is that if you randomly choose your ensemble, then because it corresponded to you randomly choose the orthonormal basics, and this orthonormal basis contain two product states would have major 0. So that's why almost surely if you randomly choose your two-qubit pure state, it cannot be optimally distinguished by OCC. So the reason we put this result, even though it's simple, is that because again, when you compare to only two-state case, then it's very interesting, because for the two-state case, you can always perfectly distinguished because of the result from Wargate and his collaborator. But when you go to the ensemble with 3 states, then it's a completely different story. Okay, and then we are interested in the product state ensemble because one of the goals is to construct more examples that have this non-locality without entanglement property. So then in the paper we have this necessary condition for optimally discriminating 3 product states. So the condition is that if lambda minima of this phi, again phi live in the orthogonal complement of the subspace spanned by the state from the ensemble, and if the ensemble can be optimally discriminated by LCC if this condition satisfied for every choice of I, J, and K. So you just look at the overlap between I with J and then I with K, and then compare with the smallest square Schmidt number of capital Phi. So I mean it's not important to memorize this, but the idea is that then we can easily construct an example that violates this condition. And if we can construct example violates this condition, then this example would satisfy this non-locality without entanglement. And actually, if you plug in the double triangle ensemble, then you will already see a violation here. So that's why we can show separable is greater than LOCC in our first result. It's because of this theory. Okay, another very interesting example is given here. So we consider one pure state and one mixed state ensemble. So the state rho theta is constructed by S plus theta and phi plus, and you can see that this 4 states span the 2-qubit Hilbert space, and like they are orthogonal to each other. And the way we construct rho theta ensure that this rho theta is a separable state. It's not difficult to check. And then we have this interesting lemma is that the state 0, 0 and rho theta given any prior probability can be optimally distinguished by separable but not LOCC. So the idea is that you transform the optimal distinguishability problem to perfect distinguishability problem from our technical lemma, and then you can just use the result from this perfect discrimination result, and to show this statement. And then there's a remark here, like if you choose theta to be pi over 4, then this state is equal to the uniformly mixture of plus plus and minus minus. And this example was used in Kobayashi, Takenaka, Yamamoto, and Imoto in a paper to show non-locality without entanglement with respect to unambiguous discrimination. Okay, and later on, I think I have sometimes, so I probably can show you, like this example also give us gap between separable known and LOCC known from this particular example. Okay, we also look at the n-copy trine. Instead of double trine, like 2 copy, we look at n copy of it. And then with this, this n-copy trine actually is closely related to the lifted trine that was studied by Peter Shaw in 2002. So what is the lifted trine? So Shaw generalized the trine state. So instead of the trine state on the xg plane, he consider lifting the trine state along the y-axis and make it a Q-tree ensemble. So you can see that this basic vector 2 is more like the y-axis. So you leave it. So you leave your trine state from here along the axis of 2, and then the angle that you lift, like sine alpha is equal to square root of, sine of the angle that you lift is equal to square root of alpha. So in a sense that I can say that alpha is, I would just say alpha is the lifting angle, because there's a one-to-one correspondence between alpha and the lifting angle. Okay?
2 is intended to be orthogonal to 0 and 1, right?
Say that again?
2 is orthogonal to 0.
Yes, exactly.
0 and 1, so you're not really lifting along the y-axis of the y.
Yes, exactly. Yeah, but yes, you're right. So here 2 is exactly orthogonal to 0 and 1. To be sure. So this is 2, this is 0, and this is 1. So the trine ensemble live in this 0 and 1. So you actually dipped it along these two directions. Okay. And then we can actually show that for any fixed n, this n-copy trine, there is a isomorphic mapping between this n-copy trine and the lifted trine. So, and then alpha is, this lifted angle depends on the copy of n. So how to show that? It's not difficult. It's because this n-copy trine, it's a three-dimensional subspace in H2 tensor n subspace, and then you can identify this three-dimensional subspace with respect to this structure. So the way we do it is that if you observe that if you rotate your lifted trine along this 2 vector, so if you rotate like this, if you rotate like 120 degrees each time, you can get to the other state. So in a sense that if you sum over xi, this vector z would have this play the same role as z. This z would play the same role as the vector 2, because when you rotate, you will stay along this direction, like by 120 degrees, you would get to the other state. So this then, once you identify this with the rho of 2, then you can construct omega I that plays similar roles, and then you can similar role as this of this trine state, and then you can represent Si in this manner. So it's very you see that it's very similar to the way you represent Shaw's lifted trine. And then we can actually show that for any finite n, this n-copy trine cannot optimally distinguish by OCC. So the way we show, let me make a remark first. This result is interesting because, again, when you consider n-copy ensemble with only 2 elements in the ensemble, this result shows that it can always be the optimal success probability can always be attained by LOCC. But again, when you go to three elements in your ensemble, then you cannot do it by LOCC. So that's why. So there's a sharp contrast when you go from an ensemble of 2 elements to the ensemble of 3 elements. So the way we do it is that because the tri-ensemble have this covariance structure, then we know that the pretty good measurement is optimal. Then from this isometry, we can immediately write down the pretty good measurement for the n-copy trine. And then we can also compute the success probability very quickly. And then in order to show that it cannot be optimally distinguished by LOCC, then you need to decomposite your pretty good measurement so that Alice would have local or orthonormal basis. So the idea is to use Worgett and Hardy's result, because the way they show you can perfectly distinguish 2 entanglement states is that Alice have some local orthonormal basis, so that if you measure in this basis, you could perfectly distinguish that. So we mimic their result, and then we show that for this for the pretty good measurement here, you don't have this kind of local orthonormal basis structure, so that that's why this n-copy trine cannot be perfect discriminated by LOCC. Okay, so this is my last slide. So maybe I would take any question now. If not, I could say a little bit about some some result that we recently have. Maybe that's also interesting. Could you turn off the screen?
Yeah.
Press again, Richard.
Which one?
Which one? The one you pressed? Yeah, one more time.
We might never be able to get it back again.
No, but that's fine. I'm done with my slide.
Yeah.
So this is
Just try and turn the board on.
So this is some result that we have found about asymptotic LOCC. So that means that, let me first give you some definition of what I mean by asymptotic LOCC. So the success probability P can be achieved by asymptotic LOCC if for any epsilon positive there exists an LOCC protocol that achieves success probability P minus epsilon. So this is what I mean by asymptotic LOCC, and it actually related to the so-called distinguishability norm. So what is the distinguishability norm? Is that so the Hermitian of H is a collection of Hermitian matrix with a collection of defined on H. And then the matrix M in Hermitian H can be decomposed into this, and then this R and S are positive, and they are orthogonal. Okay, and then let omega be a collection of two outcome P over here. Then we can define the function to be suprema over all pi in the set omega of trace pi 0 of R plus trace pi 1 of S. So this is how we define this, and then this has an operational meaning. Is it correct?
Yeah.
Okay. So this has operation. So we have a master here. This is the original work done by Weir. So given a two-state ensemble rho and sigma with probability p rho and p sigma, then if we define M to be p rho minus p sigma, then 1/2 of 1 minus this would give you gives minima error probability of distinguish rho from sigma that can be achieved among all POVM from the set omega. So you can if omega contains all general POVM, then this is equivalent to the trace distance, and this would recover the Hertzsprung bound. And then if omega is, say, the set of separable operator or LOCC operator, then you would give us the separable mean and norm and LOCC norm. I run out of time, but let me just quick. So there's one theorem that we have, and then we would just call it a day. So for 2x2 orthogonal state, rho and a pure state psi, with rank rho equal to. So the ensemble is one pure state and one mixed state with rank 2. Okay? So, and then, so perfect discrimination by asymptotic LOCC is possible if and only if. So we have two conditions. The first condition is this is a product state. And then the second condition is that the support of rho is spanned by two orthogonal product state. And then this is how we establish that there is a gap. Like if you apply this theorem to the previous ensemble that to this ensemble 0, 0, rho theta. And because they can be optimally discriminated by separable operation, but they cannot. They can, like the earlier result, our previous result is that they can be optimally discriminated by separable operation, but cannot by LOCC. And then this criterion actually, if you give it a little bit of thought, this condition is actually equal to the condition that we have. The condition that we have two anti-parallel eigenvalue, and the concurrence is equal. So this is actually equal to our previous statement of perfect discrimination by LOCC. So in the sense that for this 2x2 case, perfect discrimination by LOCC is equal to perfect discrimination by asymptotic LOCC. And then if you notice that, then this already give us the example that shows a gap between. So we would have. So if the matrix M is constructed from this, then this would give us a gap. Okay, so that's all I want to say today. Thank you.
Anyone have any questions? Lots of noise, yeah, that's good. Oh, that. Okay, so apart from that question.
Maybe one. So 2 weeks ago we heard about these, now I'm forgetting all the terminology. So we have asymptotic LOCC, and then there was something in between, no? With you have the
LOCC.
Sorry?
I think it's just called infinity LOCC.
Infinity, yeah, this is the one, yeah, indeed.
This is where
which is, yes.
limit points of what
Exactly.
would be achieved with actual sequences of LOCC protocols that were
Indeed.
long and increasing.
Right.
It contained the previous ones as previous rounds.
So it sounds like your statement that ALOCC is equal to LOCC means that you can't separate this case, since this is in between LOCC.
Yes.
But was this statement only for this case of rank 1 and rank 2? One pure and one...
Yes.
Okay, so
Yes.
it's possible that still in 2 by 2 there might be examples to separate all of these classes.
I don't think for the 2 by 2 you would have this kind of case because we somehow we look at for all possibility in the 2 by 2 and we
because this is the last one that was missing and
yes
the others
yes
are already
yes
ruled out.
yes and from there we conclude that perfect discrimination by LOCC is equal to a symptotic like ALOCC in the 2 by 2 yes
Okay.
for any 2 by 2 case
So this means that.
yes so you need to go to the higher dimension.
Okay, so shall we thank Min-Hsiu again?